Now I'd like to go through the steps to solve a minimization problem. So step 1 is to find the dual standard maximization problem from the minimization problem. We just gave you an example of that. Step 2, solve that new maximization problem using the simplex method as we have done in previous sections. Step 3, the minimum value of the objective function w is equal to the maximum value of the objective function z. So the answer to the max problem is the same as the answer to the min problem. To find out where that solution occurs, the optimum solution to the minimization is given by the entries in the bottom row of the columns corresponding to the slack variables, as long as the entry of z equals 1. Now, if the entry of z is not equal to 1, just simply multiply that row by its reciprocal to make sure that it is 1. One little note, do not divide the values of an inequality in a dual problem. This will result in incorrect solutions. For example, if you have 4x1 plus 8x2 is less than or equal to 12, in the maximization problems we could divide each one of these by 4 to get x1 plus x2 is less than or equal to 3. But in this particular minimization problem with a dual, don't do that, okay? If you do that, you're going to get different values, and the min and the max won't be then dual problems of each other. So in maximization problems, that is a valid step. But in dual minimization problems, you're going to get an incorrect solution for the variables, the y variables. Alright, so let's go ahead and try an example all the way through. So we have this minimization problem, and we need to change it to a maximization problem. So I'm going to set up my A matrix with just the variables y1, y2, and then the constants. So my first constraint is 1, 5, and 9. The second constraint, that's 2, 2, and 10. Notice that this 2, 2, and 10, I could divide each of them by 2, but I'm actually not allowed to do that in this dual problems, okay? I could have done that if this was a maximization problem. I could have done that to make my life a little bit easier, but in the dual problems, you're not actually allowed to do that. y1 and y2 being greater than or equal to 0 is required to be there in order to do this. So check, that's there, but it's not going to go in my matrix. And my last row is going to be my delete. And my last row is going to be my objective function. This one I minimize. 8 goes in y1, 16 goes in y2, and nothing is in the constant column. So if I call this A, I will need to find A transpose. A transpose is going to get me x1 columns and x2 columns instead of y's, and they will get me my new maximization problems and my new constraints. To get the transpose, I take the columns and the rows and interchange them. The first row is 1, 5, 9, so that's going to be my first column in A transpose. The second is 2, 2, 10, so that's my second column. The third row is 8, 16, 0, so that's going to be my third column in A transpose. The maximization comes from the third row. That's at 9x1 plus 10x2, which is different because it has x's instead of y's. And my constraints, the first constraint I have 1x1 plus 2x2 is less than or equal to 8. And the second constraint is 5x1 plus 2x2 is less than or equal to 16. So, and then I also have x1 and x2 have to be greater than or equal to 0. That's just a condition that has to be there. Now, normally I would take this, add the slack variables, and do the simplex method, and I will do that in the next page. But before I get to that, if I want to show you that they are going to be the same solution to the minimization problem and maximization problem by doing the solutions graphically, like we did in the previous chapter. So I want to look at their graphs to prove that the max and the min of these dual problems are truly equal. So although this isn't a normal step for this section, I'm trying to prove to you that this method is really going to work. Now I'm not going to take any time to actually graph them. I did that for you. So this is the maximization problem that we got from the A transpose. This over here is the minimization problem that we were given. I graphed both of those, And the corner points I already listed. For the maximization problem on the left in purple, we have the function z equals 9x1, just going to rewrite that here, plus 10x2. And I'm going to go ahead and put the corner points in. So we have z equals 9 times 0 plus 10 times 0, which is 0. For our next point, 0, 4, we have z equals 9 times 0 plus 10 times 4, which is 40. So that's bigger than 0. For the next point, 2, 3, that's 9 times 2 plus 10 times 3. So that's 30 plus 18, which is 48. And then the last one I have 9 times 16 fifths plus 10 times 3. And that turns out to be 144 fifths, which if you get a calculator out, that turns out to be 28.8, just so we can compare with the other ones. So it turns out that my max value for this objective function is 48. That max value occurs at the point 2, 3 for the x variables. So I'm going to label this as my max and try the other values for the minimization problem. So the minimization problem shades out because of the inequality signs. We have a few points here. I've got 0, 5, 4, 1, and 9, 0. So I'm going to plug those in my objective function for my minimization, which is 8y1 plus 16y2. So I have w equals 8 times 0 plus 16 times 5. That gets me 80. The next one is 8 times 4 plus 16 times 1. That's 32 plus 16, which is 48. And then the last one, we have 8 times 9 plus 16 times 0, which is 72. Now, this is a minimization problem because it's a W. Which one of these values is the minimum? Well, it turns out that 48 is the min, and that occurs at the y values 4, 1. So I'm going to note that as my min. What do you notice about the min and the max for these two dual problems? The min was 48 and the max was 48. So the minimum value and the maximum value is the same. That was the 48 that we talked about for both problems. Okay, so that's really interesting. That's what we had noted before, that so if you find the answer to the maximization problem, you also find the answer to the minimization problem, which is really what you were trying to figure out. The next thing we're going to do is take that maximization problem and actually solve it using the simplex method. And hopefully our answers are going to be the same answers we found when we did it graphically.